Okay. At the previous lesson, we have talked about the first order low-pass filter design in the continuous time domain. Okay, but in the reality, we need to design the second order system to get the more precise results of the filter. Okay, it's important. Second order cutoff frequency. So, what's the meaning of the second order in here? Firstly, we need to design the selecting the second order system like HC or HS is equals to the WC square form. This is the angular cutoff frequency in here, and S square plus 2 zeta WC S plus WC square. Okay, and so the natural frequency is replaced with with this cutoff frequency, because in the real-time systems or any physical or the hydraulic or the system dynamic system is just kind of the filter. Because if we apply the force, for example, and then we will get to the angle or the position or the or the some variable which is a physical entity. Okay, and so how can we set this WC in here just like this one? In the second step, for example, the select the FC is the 1000 Hertz. Okay. And you may choose the zeta, which is equals to the 0.7. Okay, and so we can assign the WC as equals to the 2 pi FC. Okay, then we have, or we can write just like this one, HS, which is equals to the 2 pi FC square form of the and divided by S square plus 2 zeta 2 pi FC S plus 2 pi FC square. Okay. And so if you are selecting the damping ratio and the cutoff frequency, you can use this filter in order to cut the frequency beyond the FC cutoff. And so we can express the whole frequency components coming from the signal to be applied on your system, and then we remove the bigger than 1000 Hertz values in here. Okay. But this is the continuous one. We need to transform this replacement or the continuous one filter to the into digital one. Okay, so how can we do that? In the section 2, we need to talk about the bilinear transform. Okay, bilinear transform. But what is that? This is the important transformation for the continuous to analog, continuous to digital representation of your filter in the mathematical formations. Okay. So if this is the case, and then we will drive the bilinear transform in here. Suppose that we have the YT is a signal with the T0 up to T integral formation of the x tau d tau. Okay, this is our representation of the integral term of the one output signal in here. And so this signal can be written as the T minus bigger T. This is sampling rate of our system, and so we can convert this system T minus T to the bigger T. Okay, and so x tau d tau can be also used in here just like this one. Okay, and so this integral is the formation of the creation of the discretization in the what? In the digital signal processing. And so, using the trapezoidal rule in here, trapezoidal rule, this integral can be represented or written as to what? Yt is closing to the what? The yt minus t in here plus t divided by 2 xt minus x, or plus xt minus bigger t, the sampling rate of this signal. And so this is the representation of the difference equation. In order to what? In order to get this continuous form in here, just like this one. And so we can write in discrete domain, okay? So this is the yn, this is the index of the what? Our algorithms. And so y minus n minus 1. And so due to this representation, we need to take the what? This signal or this value from the integral terms, because in the difference equation we need to always do what? The present formation or the present index and the future index in here. And so we can build the what? Iterative process in the what? In the discrete domain. Okay? And so plus t divided by 2 xn plus xn minus 1. Okay? So these are the discrete representation of our algorithms. Okay? And so by using these nominations or this equation yn, which is equals to the what? The y minus n minus 1 plus t divided by 2 and xn minus or plus xn minus 1. And so we can write the z transform in here, just like this one. Hz is equals to the what? The yz for a given xz. This is z transformation or the pulse transformation function. T divided by 2 times z plus 1 and z minus 1. Okay? And so if we take the what? The z transform of these terms, we will get these results in here. Okay? And so what's the meaning of this? Firstly, just remember that this is the integral process xz, and we have the one pulse transformation in here and yz. This is the what? This is the integral operation, right? And so these forms in conclusion creates the what? This form integral means that in continuous domain 1 divided by s, right? Because in the continuous time xt and 1 divided by s, and so we sum up the x signals and we produce the yt, and so this must be identical with this one. And so this pulse transfer function must be equals to the what? The 1 divided by s. This is equals to what? The t times 2 divided by 2 z plus 1 z minus 1. And so the s is also must be equals to the what? The 2 divided by t. This is the inverse values of these terms, and so z minus 1 and z plus 1. Okay? And so in summary, we have at this domain s must be equals to what? 2 divided by t times minus 1 minus z over minus 1 and plus 1 plus z minus over 1. Okay? And so this is called to the what? To bilinear transformation. Okay? This is a simple idea. If we have in the continuous domain, we have the integrator in here with the values of the 1 divided by s, and so we can turn or produce these terms into the what? Into the discrete form or the z transform form. But with what? With using the trapezoidal rule. For example, if you are using the forward difference or the backward difference or the center difference equation, you will have the what? The some other operators in here, except from the what? The this representation. But the bilinear transform is what? Is looking like that. Okay? And so, how can we understand this process in here? We need to what? We need to create an example session about this. And so, we need to write the example in here, just like this one, x. And so, let's consider to what? To hs is equals to 1 divided by rcs plus 1. This is a low pass filter, right? And so, then obtain the what? Obtain the discrete form using bilinear transformation. Okay? And so solution is simple. First of all, we need to what? For the cutoff frequency. The FC must be equals to what? 1 divided by 2 pi RC. And we have the what? We see is equals to what? 2 pi times 1 divided by 2 pi RC, which is equals to what? 1 divided by RC. Okay? This is the angular frequency or the cutoff frequency. Just remember that. Angular frec, not a normal one. Okay? These are the results. And so, the transfer function in the second place, the TF, can be what? This one. HS is equals to what? The 1 divided by RC S plus 1. And so 1 divided by RC divided by S plus 1 divided by RC. And so this is equals to what? The WC S plus WC, guys, right? This is our basic implementation about this filter design. Okay? In the second place, we need to apply the what? Apply bilinear transform. And we get the what? The S must be equals to 2 divided by T times 1 minus Z over minus 1, 1 plus Z over 1. And then we have in the what? H design of filter Z in this domain in here right now. This must be equals to Z. This is the Z transformation or the pulse transformation of this system. And so WC divided by 2 divided by T times 1 minus Z over minus 1, 1 plus Z over minus 1 plus WC. Okay? This is our filter representation in the what? In the discrete domain. Okay, guys? So, at the third place, we need to reorganize these equations in here. First of all, if we have this representation, and then we can reorganize our filter like the what? The HDZ must be equals to what? The WC divided by 2 divided by T times 1 minus Z over minus 1, 1, Z over minus 1 plus WC. Okay? And so, in order to remove these terms, and then we need to multiply with what? The 1 plus Z over minus 1, 1 plus Z over minus 1. This does not change anything on these systems. Okay? And so, the result is simple. WC 1 plus Z over minus 1 divided by 2 divided by T times 1 minus Z over minus 1 plus WC 1 plus Z over minus 1. Okay? This is our filter representation about what? About this signal representations in here. Okay? And so, how can we summarize the whole equations in here? Just see that the R equation must be equals to the what? The HDZ must be equals to the what? WC times 1 plus Z over minus 1 divided by 2T WC plus 2 divided by T minus WC times Z over minus 1. Okay, this is the our basic representation of the digital low pass filter in terms of the in terms of the Z domain formations. Okay, and so how can we analyze these signals in here? Because if we have these informations in here just like this one, and so we need to apply the pre-warming conditions, right? So in the third place we write that the pre-warping cutoff can be defined to satisfy cutoff frequency is coming from the cutoff property, okay, non-linear to linear one, because the R filter is in the form of the linear domain in here, and so this can be set with the WC over comma is equals to the 2 divided by T times tangential components of the WC T divided by 2. This is a pre-warping cutoff frequency properties in here, just like this one, and so we need to replace this WC with this one, because the linearity of this filter maybe decreases the our performance of the filters. But if we change this filter with these nominations, and then we can write that the HDZ can be equalized to the WC comma times 1 plus Z over minus 1, and so 2 divided by T plus WC comma plus 2 divided by T minus WC comma times Z over minus 1. This is the this is the last representation of the R filter design, okay? But in the final form we need to write this equation as a different one, because if we want to implement this algorithm on the embedded systems, and so we need to write out to this one, YZ divided by XZ, which is equals to the these terms, WC comma plus WC comma Z over minus 1 and 2 divided by T plus WC comma plus, and so 2 divided by T minus WC comma times Z over minus 1, okay? And so we need to convert this form into the HDZ is equals to the B0 plus B1 Z over minus 1, and then 1 plus A1 Z over minus 1. This is the simplest representation of the low pass filter in the in the correct order of the R formations, okay? And so this YZ divided by XZ can be represented right now with the with these terms. Firstly, this is the omega C divided by 2. I'm sorry, there's not enough space to write these equations, and so the YZ divided by XZ can be represented with the with these terms, okay? And so the WC comma divided by 2 divided by T plus WC comma plus WC comma divided by 2 divided by T plus WC comma times Z over minus 1, and so we have the 1 values in here because we divide the whole terms into the into this parenthesis, and so we have 2 divided by T minus WC divided by 2 divided by T plus WC comma times Z over minus 1, okay? And so in this equation this is equals to the this is equals to the B0, this is equals to the the B1, this is equals to the the A1, okay? So If this is the case, and then the R formation or the difference equation can be given with what? With this formation. YZ times 1 plus A1 Z over minus 1 equals to the what? The XZ times B0 plus B1 Z over minus 1. Okay? And so, in difference equation, yn plus A1 times yn minus 1, which is equals to the what? The B0 times xn plus B1 xn minus 1, right? And so, in the last form, we will have the yn, which is equals to the what? The B0 xn plus B1 xn minus 1 minus A1 yn minus 1. Okay? And so, this is our difference equation to be implemented on your algorithms or your code. Okay? And so, if you put the B0, B1 and A1 in terms of these equations or these values with a specific what? The cutoff frequency, and then you can feed the values of the x as the input, and we will get what? Our filtered response in the what? In the embedded systems. Okay? That's all. This is the representation of the what? The first order low pass filter design in the what? In discrete domain, guys. Okay? And so you need to follow this process into the what? Into solve your equations or the sum values, and then you can easily use the bilinear transformation to what? To your continuous filter to be what? To be implemented in the discrete one. Okay? That's all.